We've got 4 presentations, 3 long papers and 1 short paper. Is the speaker for the short paper here? Okay, we do have all 4 presentations. All right, so we're going to start out with Bastian Ziegabau, who's going to be talking about making hybrid plans more clear to human users.
Okay. So, recently planning technology has been applied to domains such as emergency planning, assistance of cognitively impaired and elderly people, and support daily activities. So in these domains, the planning system provides recommendations for when and how to act to human subjects who might be just more or less competent in these domains themselves. And this leads to the problem that the human user might question these recommendations. And if the system is not able to answer these questions, then mistrust in the system's competence could be provoked, and maybe even the plan will just be disregarded. So in our opinion, a planning system must have the ability to give reasons for the decisions it made and present them in a comprehensible manner to thereby build trust in the system's competence. So our contribution in this work is the specification of a framework for the generation of what we call raw plan explanations. So we can imagine that a raw explanation represents the content of an actual humanly readable explanation. So the raw explanation could be used as input to, say, a natural language generation system that then produces the actual readable explanation. So in this framework we have implemented the explanation for the existence of actions and order of actions. So we are now able to answer questions by the user such as, why do I have to execute this action A from the plan? Or why do I have to execute this action A before that action B? And based on this framework we have implemented a prototype system that can generate such raw explanations. The basis for my explanation framework is a hybrid planning framework which combines aspects from classical and hierarchical planning. In this framework, the planning problem is simply triple. First we have a set of tasks which can be partitioned into sets of primitive and abstract task schemata. The primitive tasks simply take over the role of the operators from classical planning, and the abstract tasks represent high-level activities that are usually composed of several primitive tasks. Then we have a set of decomposition methods. These define predefined solutions for the abstract task in the form of small plans. So during planning, the abstract task will be solved by just replacing them with one of the plans from their respective methods. And finally, we have an initial partial plan that needs to be decomposed by the planning system in order to find a solution. And typically, we have 2 artificial plan steps, init and goal, where init has the initial state as effects and goal has the goals as preconditions. So a partial plan is a for tuple with sets of plan steps, ordering and variable constraints, and most importantly for us, a set of causal links. A plan step is simply a pair of a unique label and a partially instantiated task. The ordering constraints define a partial order on the plan steps to represent the order of execution. The variable constraints can be used to bind the variables from the partially instantiated task to other variables or constants. And finally, a causal link between plan steps S and S prime over precondition P of S prime represents the establishment of this precondition by the effects of S. Such a plan is a solution to a planning problem if every precondition of every plan step in the plan is established by one of these causal links. Seconds, none of these causal links are threatened. So that means between S and S prime, no plan step may be ordered that has P in the delete list. So these 2 conditions ensure that the plan is executable and reaches all the goals. And finally, the plan may only contain primitive tasks, and it must be able to obtain it from the initial plan by decomposing the abstract plan steps and by inserting plan steps, causal links, ordering and variable constraints as we like. So most important for this talk is we have causal links to represent the establishments of the preconditions, and we are decomposing abstract plan steps via these methods. Okay, this is my one example for this presentation. It is taken from a new domain which we call smartphone, and in this domain the planning system gives advice to the user of a smartphone on how to organize tasks from his daily life. So in this case, the goal of the plan is simply to send a photo from the smartphone to some other person in any way possible. So here, the plan works by first entering the photo album, then selecting a picture from the photo album, choosing the send by email function from a context menu, and so an email program will pop up, and in this program we choose a recipient and press send. Then we have, so these are basically the primitive plan steps. And between the plan steps we have causal links depicted as these arrows, and they are annotated with the name of the precondition that is established by the causal link. So in this example, enter album establishes the precondition in album mode of select pick. Then this plan was constructed by decomposing two abstract plan steps for displaying the picture and then sending it. And these are connected to the plan steps that were inserted into the plan through their decomposition by these diamond-shaped arrows. And they are annotated with the name of the method. So the abstract plan step display pick was decomposed with the method display pick via album into these two plan steps. And finally, I use an artificial task called top, which simply decomposes into the initial plan of the original planning problem through this method mtop. This is just a little trick that allows me to formulate part of my explanation framework more elegantly later on. Okay. So, the basic framework for plan explanation. We use a first-order logic axiomatic system. And in this system, we formalize information about the plan, the construction process that led to the plan, and basic arguments for the explanation in the form of axioms. So in this framework, constructing an explanation means to find a proof for a first-order logic formula that represents the aspect of the plan that we want to explain. And since all elements of this axiomatic system are based on the problem specification, the underlying planning formalism, and the construction process that led to the plan, we can say that our explanations are correct with respect to the underlying planning system. The most basic elements of our axiomatic system represent the causal and decomposition structure of the plan. So the causal structure describes how in the plan preconditions of plan steps are established by the effect of other plan steps. And since this establishment of preconditions is in our planning formalism explicitly represented by these causal links, we get for every causal link between a plan step S and S prime over precondition P, one atom with corresponding arguments over this predicate symbol CR, which is simply short for causal relation. And so in the same manner, the decomposition structure describes how during planning abstract plan steps were decomposed into primitive plan steps. So for every plan step S that was introduced into the plan by the decomposition of an abstract plan step S prime through a method M, we insert an atom with corresponding arguments over this predicate symbol dr into our axiomatic system, where dr is short for decomposition relation. So I will give some examples. So this is a small excerpt from my running example. And so here we have, for example, a causal link between enter album and select pick over this precondition in album mode. So therefore we simply get an atom with enter album mode, and select pick as arguments over this predicate symbol CR. So this is very simple. And in this plan, send pick was decomposed with the method send pick by email into this plan step press send by email. So we get an atom over predicate symbol dr, which with these two plan steps and the precondition as arguments. And you can think of these atoms as the elementary building blocks for our explanations. And now I will formulate the rules by which we combine these building blocks to form an explanation. Okay, for this I introduce a new predicate symbol called nec, which is simply short for necessary. And nec of S should denote the information that the plan step S is necessary for this plan to be a solution. And I want to make clear that this does not mean that there cannot be a solution plan for the same planning problem which does not have S. It simply means that we cannot take S out of this plan without spoiling the correctness of this plan. For some reason this seems to confuse some people. Okay, so this means in my framework to construct an explanation for why the user has to execute plan step S, I have to construct a proof for this atom, and then I can take that proof and insert it to, say, a natural language generation system, and that will produce the actual readable explanation. Okay, so there are 4 ways to show that neg of S is valid in the axiomatic system. First, let's say there is a goal, and this goal is actually established by the effects of S. Then I can really say, okay, I cannot take S out as it is really necessary for this plan to be a solution. Second, I have a plan step S prime, and I have already shown that this is necessary. Then if S establishes one of the preconditions of S prime, I can also say, okay, I cannot take S out as it's really necessary. Then the second 2 axioms do the same for the decomposition relations. So if S is a substep of top, which means S is a plan step from the initial plan of the planning problem, then S must really be there because it was specified by the user that it has to be there. Specified by giving the original problem formulation. So this is actually why I use this plan step top, because it allows me to represent with the decomposition relation that the plan step was from the initial plan. So and finally, if I have a plan step S prime and I've already shown that this is necessary, then I can say a substep S of S prime must also be necessary. Okay, I will give an example. In my running example, I want to explain why this plan step anti-album is necessary. So I have to show that this atom is valid in my axiomatic system. And I have these 4 axioms available and the causal decomposition relations from the plan. So now I have to decide which of these 4 axioms I want to use to show this. And usually I can use more than one of these, so there are usually many ways to explain a plan step. In this case, I will use the second one. So this one says to show that anti-album is necessary, you have to find a causal relation between anti-album and some other plan step S prime, but then you have to show that S prime is necessary. So in this case, I use a causal relation between anti-album and select pick, but then I have to show that select pick is necessary. Okay, so how do I do this? I use again the second axiom. So I choose in this case this causal relation between select pick and present by email, but then I have to show that that one is necessary. Now I could use the second axiom again, but just for a matter of taste I choose the 4th one. So this just swaps the causal relation with the decomposition relation. I use the one between present by email and send pick. And finally, send pick is a substep of top, so I can use the 3rd axiom, which says if a plan step is a substep of top, it is necessary. Okay, so obviously nobody can really read this. So I will show you what we would imagine what this would look like if we transformed it to a natural language, which we cannot do as of now, but we hope to do it in the future. So you could read this as follows. Entering the album is necessary to select the picture. You must select the picture in order to use the present by email function. And that is a necessary substep of sending the picture, which is part of your own initial problem specification. Okay. So now we can construct some simple example explanations. But I'm not quite satisfied yet. If you explain something in real life, you can never give all the details. You always have to explain on a more abstract level, and you can just go into details every here and there, depending on what you find most important. And we want to be able to do the same thing in our explanations. And we have actually partially tackled this already by allowing the use of these decomposition relations. So these allow us to go to a more abstract level in the plan. But now we have a problem. As I mentioned before, the causal structure so far contains causal relations for each causal link in the plan. But depending on the underlying planning formalism, the planner does not have to add these causal links for the abstract plan steps. Only on the level of the primitive plan steps I can be sure that the causality will be completely specified in the plan. This means that in general I can only explain an abstract plan step through these decomposition relations. So that means once I have gone to the abstract level, I can only get to even more abstract levels, so I can never get back down to the primitive level of explaining the plan. And we want to solve this as follows. What we want to do is we want to calculate the causal relations for the abstract plan steps ourselves within the framework. So if the planner is not doing this for us, we just do it ourselves. So for example, let's say we have a causal relation between select pick and percent by email over this precondition. Then, and also we can see that select pick is a substep of display pick. Well then we might just as well say in explanation that display pick establishes this precondition pick selected for percent by email. Or the other way around, we could say that select pick establishes this precondition pick selected for send pick. So in this way we let the abstract plan steps inherit the causal relations from their substeps. And then we could use these inherited causal relations just like any other causal relation in an explanation. And this is actually captured by these two axioms. So this first axiom says if you have a plan step S double prime, in this case select pick, which is a substep of display pick or S in this axiom, and you have a causal relation between S double prime and S prime, in this case select pick and percent by email, you can actually derive a causal relation between S and S prime, so in this case display pick and percent by email. And then the second axiom allows us to derive this causal relation, and of course we can let this causal relation be inherited again to even get a causal relation that is only between abstract plan steps. So now we can go back and forth between the levels of abstraction in the plan as we like. Okay. Okay. So I guess I have enough time to go a little bit over this. So now we can let abstract plan steps inherit these causal relations, but sometimes this will produce explanations that do not sound very reasonable. So for example, in my running example, I can derive these causal relations between send pick and the goal. So if I use these in an explanation, it would sound like this. You have to send this picture because you wanted to send some email. Or if I use the other one, I would say you have to send this picture because you wanted to attach this picture to some email. So using either of these explanations alone would not sound reasonable. It is actually the high-level goal that we wanted to transfer this picture to that other person that is achieved by these two goals in combination. And we would like to reflect this in our explanations. So what we can do is we introduce a set of decomposition axioms, and these define what you could call high-level state features. So in this case, we say that transferring a picture is equal to attaching that picture to an email and sending that email. Or, for example, to printing that picture and sending it by fax. And now we want to derive causal relations over such an abstract literal as this. And this is actually made possible by these two axioms. I guess I don't have enough time to explain them in detail. But using these, we could, for example, derive this causal relation. And if we use that in an explanation, it would sound like you have to send the picture because it was your goal to transfer this picture to that person. Which sounds a little bit trivial, but is more reasonable than using either of these causal relations. Okay, we have implemented a prototype system that will generate explanations as specified by this framework. And the good news is, doing this seems to be computationally quite easy. So usually we can generate just thousands of explanations within a few seconds. So the question is not how to generate an explanation efficiently, it is how to select among these large abundance of explanations. So there are a few quality features that come to mind, such as the size of the explanation, type of argument used, the means we have available for presentation, so if we can display only text or graphics, or if we only want to give out some speech. And of course, it is important to know what knowledge the user has about this application domain. For example, to decide on what level of abstraction you want to explain what part of the plan. Okay, in summary, we believe that communication of plans is a crucial ability for the acceptance of planning technology in a wider range of applications. So here, as a first step, we have presented a general framework for the generation of explanations, and we have instantiated this framework for the explanation of plan steps and the ordering of plan steps within the plan. I didn't go into this in this talk, but it is in our paper. And we believe that future work should deal with first the presentation of these explanations and how to select a raw explanation from this large amount of explanations that we can generate. Thank you for your attention.
So is it time for some questions? Andre?
Is it also possible to use these ideas for finding optimal goals, for finding optimal plans, for example, on cost? You want to find actions that has to be the best plan.
I wouldn't think so, because it analyzes the plan that's already there. So I don't think so. At least I've never thought about it.
So one of the things that I've come up against in this type of thing is you show people a plan and they want to know why this action isn't used. Mm-hmm. Right? They want to say, well, I would have used this action, but it doesn't appear in the plan. And so is there any extensions that you can see to actually start reasoning about why this action is not in the plan?
Okay. So the good thing about this type of reasoning we do is that it is quite efficiently possible. What you suggest would, I suppose, mean that you would have to just plan again, but say, don't use that action. And so this would be computationally much more difficult, I think. I know there has actually been work about explaining why we couldn't find a solution for a planning problem in a particular situation. So I think that would more fit into with that idea. But yeah, I think that would also be good to use such information in an explanation.
Okay. Any other questions? Okay, thank you. Okay, so the second talk in this section is going to be given by Simon Parkinson. It's the application of automated planning to machine tool calibration.
Okay, my name is Simon Parkinson from the University of Huddersfield, and I'm going to describe our problem of machine tool calibration. So I'm going to start by giving an overview of what the problem is. So for those who don't know, a machine tool is a mechanically powered device which is used for machining components. So you have two examples, one on the bottom where we're manufacturing the skins of an aircraft wing, one on the top where we're making very small false teeth. I mean, machine tools are used for a massive variety of components, so I don't think you could go through your daily life without using something that's being machined. Now, machine tools have a working volume, and you need to establish the predictability of the machine throughout that working volume, because all machines have errors. So, and the demand to manufacture parts of a higher accuracy results in the requirement of machines that are more accurate, because you can only make artifacts that are as good or as good as the machine's accuracy. So making the machine more accurate, you can manufacture more accurate components. And I'd just like to show you this machine at the bottom here, which has a very large working volume for making these turbines that you can see on the right. But it has a volumetric accuracy of only 20 microns. Just put that into perspective, the average human hair is 70 microns. You can see this machine is very accurate and highly predictable, but this machine costs well over £2 million to buy. So all machine tools have errors because they're made up themselves of manufactured parts, and when you manufacture something you make it to a tolerance, and these tolerances propagate through the machine and then you get the error. So you can see on this picture here you have the machine's expected position versus its actual position. So the process of calibration is the process of understanding all the different error components that come together to make this deviation. So performing a machine tool calibration is an expensive task. The machine needs to be taken out of service for quite a lengthy period. So you really need to make sure that you get it right first time. And on the bottom here we have a picture of a machine that has a 72-metre traversal length, and you have to measure all the geometric errors across that entire length. And that's going to take a long time. You've got a lot of measurements to do. The machine's going to be out of service for at least a week. You need to make sure that all the results you get are usable, otherwise you've wasted your time. So expert knowledge is certainly required. You need somebody who's very experienced in this area to come up with a calibration plan. So just to summarise, calibration can be broken down into the following sub-processes. First of all, you'd analyse the machine's configuration to determine the geometric errors. Then you'd prioritise these, which ones are more important depending on the machine's configuration and what you're manufacturing. You'd select the best measurement method, and then you'd select the best equipment for that measurement. So first of all, we'll just look at the machine's geometric error. So a machine tool will often move in two-dimensional space, X, Y, and Z, and then you also have two rotary heads on the end of the tool. So it's kind of familiar to like the robot action that you'll all be familiar with, but instead of this you move normally a big table for stability reasons. So with a linear axis you have the standard 6 degrees of freedom, and you need to measure each one of these error components individually, and then from this you can establish the overall volumetric accuracy. And the order in which these axes are stacked on the machine determines the propagation of error. So if you have a linear axis then another one on top, the first axis, the error propagates through to the second one, so it's more important to measure this one first. So with measurement methods, there's a lot of different standards available, but we use the ISO 230. And in there, there's two methods here, just for an example, for measuring the straightness of a linear axis as you traverse. One of them uses, on the left, uses a reference edge and a dial test indicator, so as you move you can see the deviation. Where the one on the right uses laser interferometry, which is good for long travel, where you'd use a straight edge for very small machines. So with the measurement methods, a lot of the instrumentation you can measure different error components. Like here we have two pictures where we're using laser interferometry. The one on the left we're measuring positional deviation, the one on the right we're measuring vertical straightness. So once you've got the laser aligned parallel with the axis, and then you've got the optics aligned with the laser, it's often easier to change the optics over to measure a different error component rather than getting some new instrumentation and start again. So you can save a lot of time by optimizing the sequence of measurements depending on what instruments you're using. So with some of the measurements, you can measure more than one error component at one time. So say if you're measuring the horizontal straightness of an axis, you might also be able to measure the linear positioning if you can get two instruments on there at once. But this depends on if there are any physical limitations of the machine and its environment, if there's any instrumentation interference, and if the measurement parameters themselves are compatible, so the speed at which you traverse and the number of samples you take. So we thought it was a good idea to use automated planning to try to produce the optimal sequence of calibration tasks, so we could reduce machine downtime. First of all, we started out with a hierarchical task network with the SHOP 2 architecture, because we thought the way that machine tool calibration could be broken down into smaller subtasks would be an ideal solution. And then we moved on to a PDDL model with the LPG-TD, which I'll explain why in a minute. So with the HTN, we have an abstraction here where you can see how we broke it down. This is very abstract, but just to show that it could be nicely represented as subtasks. But then we moved to the PDDL encoding because it's easier in PDDL to represent time and concurrency. So in our PDL model, and also you can use a larger variety of planning algorithms. So in our PDL model we use quantification numbers, time initial literals, and also derivative actions, obviously because we're trying to optimize in terms of time. So time is very important. So in our model we have several temporal constraints, so I'll just go through a few of them here. So if we're planning to do multiple measurements on one axis, you need to make sure that all the instruments that are set up on the axis have to be on the same axis for more measurements. And each instrument will have a maximum number of tests that it can perform simultaneously, so how many degrees of freedom it can measure. And on some axes it's not possible to use certain equipment simultaneously because of instrument interference, so you wouldn't have like two lasers because the beams might cross and it just wouldn't work. And then also testing can happen over a number of days, but we need to schedule it into an 8-hour period because you wouldn't want to get to the end of the day and have a measurement set up but not finished, because it's not good for measurement traceability. You need to optimize the sequence. So also we have some spatial constraints on the machine's design and location, which can prevent the use of some instrumentation. You might go to an industry where the machine is in such an awkward position and you just can't set up your instrumentation outside of it to get the laser in, or the machine's volume might be so small that you just physically can't get in there, so you have to be very careful of what you use. And also the operating range of the instrument must be greater than the desired traversal length. So in our model we have three types of error. Objects, so we have the axis, instrument and error. And these two diagrams here just give an abstraction of how our operators are manipulating the objects. So you can see with the instrument, it can set up to measure an error, but then it can also adjust to measure another error. And it can be removed for a new instrument to come in. And with the error object, it's either set up, adjust or measure. So in our model, we have two plan metrics. First of all, time. We want to minimize the total time of the calibration. But also, if you don't have enough time to perform a full calibration, you want to optimize in terms of what you're measuring. So we assign an importance value to an error component from the way that they propagate through the machine's kinematic chain. And then if the time's not available, we select the most important ones first, so that you can calibrate the most significant errors to try and improve the accuracy this way, and then you can come back later on and measure the ones that are not as important. And to do this, we take into consideration what the machine's actually being used for. So if it's a really large volume, but you're only using a certain part of that volume, we'll concentrate on measuring there rather than the other parts. So we take into consideration the customer's requirements. So in our initial state, we have all the setup and adjustment times for the instrumentation, which instrumentation can measure which error, and all the errors that need to be measured, and the importance of each axis and error. So then in our goal state, we can either pose all the error components that we want to be measured, or if we don't have enough time, then we pose an empty goal and leave the planner to try and select the best ones, the most important errors to be measured. So here's just a comparison of our two models at the top there between the SHOT 2 and the LP GTD, and you can see that there's very little difference. But the one beneath is when we enabled concurrent measurements, so that multiple measurements can happen simultaneously. And you can see that this significantly reduces the time. And this is interesting because a lot of engineers who calibrate machines don't really think of performing measurements simultaneously. They like to do it sequential. So when we produce some of these plans, they were quite surprised that we can optimize in this way, and they found it quite beneficial. So I thought I'd just go through a case study with one of our industrial partners of a 5-axis gantry machine, which has a total of 41 geometric error components. And we have two expert plans, one from an academic and one from the industrial partner. And then we have the HGM produced plan and the PDDL